Good afternoon, everybody. Welcome to the jetspace. Today, we're very thrilled to host our first guest lecture today. Joining us is one of our own. He's an American topologist and differential geometer currently pursuing his PhD. He leads us into the beautiful subject of knot theory. So, joining me, giving him a warm welcome. We're grateful for his contribution to our community, and I encourage you all to be an engaged audience, ask interesting questions, be respectful. Without further ado, the floor is yours.
Awesome. Yeah. So during this talk, if any of you have questions, be sure to just like tell me, like unmute or something and ask, and I'll be happy to clarify. So this talk is going to kind of be split into three parts. So there's what is a knot, like what are we trying to classify with knots in knot theory, and then the algebraic topology of knot theory and Seifert surfaces, which give knot invariants. And then we're going to take a quick look at knotted surfaces of embeddings in S4. So we're going to be looking at how can we bend manifolds into S4 and what are some of the ways that we can deal with these weird topological behaviors that can come up since it's a four-dimensional manifold. So knot theory is basically for the whole talk, I'm going to be writing S1. That's just going to be the circle, the topological circle. And knot theory asks basically what are the different embeddings? What are the different embeddings of S1 into R3? I mean, you can of course do different manifolds, and that's going to be a question in knotted surfaces, like what are the possible ways that we can embed things in knotted like manifolds into other manifolds. But the question is, for simple classical knot theory, is just the circle. Uh, so the question now becomes, well, what do we mean by different embeddings? So, for example, we want to look at there are two embeddings that are pretty classical. We just the standard circle, and then there's the trefoil. The trefoil, which looks something like, if I can draw this properly. This is a little difficult to draw. Okay, the trefoil knot. Somehow, or I guess I did this a little wrong. It should be just a little bit like, oops. Let me undo that. Is there any way to erase? Here, over here. Imagine that this part is a crossing. Okay, so for we kind of have an intuition that somehow this knot, the trefoil knot, is not a simple circle. And our intuition is probably coming from, well, if you take a trefoil knot in real life, like there's no way without, we want to somehow classify how there's no way to turn a trefoil knot from a circle into the normal circle without crossing lines. So this is somehow going to be how we're going to construct our equivalence class. And so one might naively think that we could choose homotopies between a homotopy between the trefoil knot and the circle, where a homotopy means it's just a map S1 cross I to R3. But the problem with that, we want to, in some sense, measure that we cannot cross, like we can't have anything that like this where the intersection, we have an intersection with the knot itself, a self-intersection. So one way to say that these knots are equivalent is if we look at all the functions that are homotopies through embeddings. So for example, we could have homotopies through embeddings are, for example, we can look at S1, and over time we can just be bending S1 and keep on bending it to do weird things, but it can never have a self-intersection.
Oh
Homotopy through
yeah,
basically no self-intersections. Was there a question?
yeah. Keep bending it. Keep bending it.
Keep bending it. Uh, okay, let's see if we can maybe get something that looks, we can bend through like this.
Bend it harder. Bend it harder.
We can do something like that, and it can like bend through itself and something like that. Something, as long as there aren't any self-intersections, that means that we're looking at knots up to bending through no self-intersections. Now, the problem with this definition, this is still a little too naive, because we could have insane, like, pathological embeddings. So, for example, if you take the trefoil knot, it looks something like this again. I can't draw the trefoil knot perfectly, but I think it looks, yeah, it looks like that. We could have a trefoil knot. We can construct an embedding where we take a trefoil knot. We go to this map. Uh, this map, and then it goes through here. Then we do another one. And it goes through here. I need to undo that last one just a little. Sorry, these embeddings are a little hard to draw, but you can have, you can keep on repeating this process. And you can create, if you keep on repeating this process on each of the crossings, you get a pathological embedding of a knot. And so we want to somehow avoid these pathological embeddings, because if you've ever seen Alexander's horned sphere, this is very analogous construction to Alexander's horned sphere. Like if we keep on repeating this process of making these small like little loops here uh, on each of these little before all the intersections, we can get in a pathological embedding. So we want to somehow avoid the pathological embedding. And in classical knot theory, there are two ways to avoid these pathological embeddings. And that is one, there are two remedies for this. One is the idea of combinatorial knot. And two is smooth knot. Okay, so combinatorial knots, what they are is, so going down, a combinatorial knot, oh, a combinatorial knot is a one-dimensional simplicial complex in R3 that is homeomorphic to S1. So what is a simplicial complex? Well, in one dimensions, you can think of a simplicial complex as basically a graph. So what are examples of combinatorial knots? For example, the unknot, which is just a trivial embedding, will look like this, just a graph. The trefoil knot, we can, like, for each of these edges, add one of the we can add one vertex, and then this is of course in 3D. Oh, I did that wrong. And then it should be. Oh, this should go here. This should go here, and this is here. Something like that. But we can kind of create I can't draw it correctly, but we can create a combinatorial version, like a graph version of these knots. So it doesn't really matter, but that's an example. Also, and another example of an unknot is we can subdivide edges so that we get something like this. We could have a square or something more like a pentagon. It's a graph that represents our knot, that is homeomorphic to our knot. Okay, so that's the combinatorial knot. And two, a smooth knot. And first of all, what are the equivalences of a combinatorial knot? Let's start that. So an equivalence of combinatorial knots is a homotopy through linear maps. Is a homotopy through linear maps from the first knot to the second knot. This is called a linear isotopy. Okay, so linear isotopies of knots is going to be our equivalent. That gets rid of all the pathological behavior of the limit of these embeddings here. And two, for smooth maps, smooth knots. Okay, a smooth knot, is a diffeomorphism. Is a diffeomorphism of S1 onto some subset of R cubed. So that's basically a smooth embedding. It's a smooth embedding of S1. So most people, when they think knot theory, they think smooth knots, because that's generally the most applicable. Turns out the knot theory of combinatorial knots and smooth knots is the same. Like the category of these is the same. So what is an equivalence of smooth knots? Well, it's basically the same thing. An equivalence of smooth knots is a homotopy through diffeomorphisms. From the first knot to the second knot. This is called a smooth isotopy. In general, I'm just going to call them isotopies. It's going to generally be easy to see which of the types of knots I'm using because of the statements of the theorems. And so I'm just going to call a smooth isotopy or a linear isotopy just an isotopy. Okay, so we have an exercise to the audience. If you want to talk to me later about these, I'd be happy. The exercise.
Excuse me.
Yeah.
So I'm interrupting. Can you maybe move up a little bit more upwards? I'm a bit slow with writing down, and I was still taking notes.
Okay, so move up.
Yeah, just a little bit. That was fine. Yeah, you can still only the last part is fine.
Okay.
Thank you.
Exercise 1. Show that smooth / linear isotopies form an equivalence class. Oh, an equivalence class. Okay. So I'm going to leave that as an exercise, but that is just a general. It's a pretty easy exercise to prove. Okay. So now the question becomes: we now know what it is that makes two knots equivalent. What is now the question is: how can we determine if two knots are equivalent, though? Like, is there some algorithm that we can do to tell if one knot is going to be equivalent to another knot? Turns out, yes, there's an algorithm. That's not in the scope of this talk today. The algorithm is like 100 pages long, and it is extremely complex, and I don't even fully understand it since I'm not a knot theorist every day. But a mathematician named Reidemeister was interested in this problem, and he was able to prove a very wonderful theorem about knots that tells you how two knots can be equivalent. So we're going to work towards what's called Reidemeister's theorem, and we're going to need a few definitions for that. So definition: a set x of r cubed, or of Rn. Sorry, yeah. Okay, a set of Rn is said to be in general position. To be in general position if for all 2 less than or equal to I less than or equal to n plus 1, and I points x1 through xi in x I minus 2 coplanar. That means that if you take any I point, like any number I between 2 and n plus 1, I of these points, not be in a I minus 2-dimensional plane. So an example of, for example, R2 of a non-coplanar set, or a non-general position set, would be points like this, this, and this. These all lie in a one-dimensional line. But they are in general position in R2 if we put them in something like this. That's what general position means. So the reason why we care about general position is if we take a combinatorial knot. So we take a projection. We can take a projection I going from R3 to R2 by pi of x, y, z equal to x, y, then for a combinatorial knot, let's say it's f going from the boundary of the 2 simplex to R3, pi of f, or pi composed of f, will have transverse self-intersections. Now, what do I mean by transverse? Well, transverse basically means that if I have a self-intersection, we cannot have a line lying over a line. So we can't. We have to have something that crosses itself, like, completely. And we can't have, for example, let's say we have a knot that looks like this, straight down. Let me draw this better. Straight down, out, and then kind of diagonal. This is we can't have basically the projection. You can't have this whole line here projecting onto a single point. The transverse just basically means that we can see all the lines independently. So when we project down, we can see every single line. None of the lines are squished down a dimension. They're all crossing each other completely. They're not lying over one another. So that's what transverse means. So, and we define, so this is bad. I should draw this a little better so that people can get a better understanding. This is a straight down if we have our axes like this. Okay, so we define a diagram of a knot f going from boundary of delta 1 to r cubed is pi composed with f, where pi goes from r cubed to r squared by pi of x, y, z equals x, y. Okay, so now we can go to Reidemeister's theorem. Reidemeister's theorem this is a very classical result. So given a combinatorial knot, given two knots K1 and K2, then K1 is equivalent to K2. Sorry, I missed a condition. Oh, and an exercise. Okay, let me really quickly go through this. So exercise 2, show that every combinatorial knot is equivalent to a combinatorial knot in general position. Okay. Okay, now Reidemeister system. Meister system. Okay, let K1 and K2 be not in with vertices. I guess sorry, with vertices. Vertices in general position. Sorry. Let K1 and K2 be knots with vertices in general position. In general, the vertices in general position. Then K1 is equivalent to K2 if and only if there are finitely many moves, or there are finitely many knots Ki for I in the natural numbers, such that Ki plus 1 is derived from Ki from one of the following changes. Okay, so let me zoom out a little so that there we go. That might be a little easier. Oops. Oh, my mouse is, there we go. Okay. 1, we have, you can take 2 vertices and you can bisect the line up top and move the vertice out. So you can get this. 2, you can take something like this, and you can turn it into this. Into this. Okay? And then 3, you can take a crossing. You take this. You take this. And it becomes this. Making sure I get the diagram right. Okay, yeah, it becomes that. Okay, so those are the three types of Reidemeister moves. They're called Reidemeister moves. Actually, it turns out once you know these moves, it's not hard to prove Reidemeister's theorem. Reidemeister's theorem. Okay. Okay, so now we know, and turns out using Reidemeister's theorem, you can construct an algorithm. It is possible to construct an algorithm that determines whether two knots are equivalent or not. So now the question is, though, can we find an obstruction? Given two knots, is there an easy way that we can calculate like some invariant that tells us whether or not two knots are not equivalent? So that's where we move to invariants. Invariants. So here are a few invariants. The crossing numbers. Crossing number. Is the minimal number of crossings of the equivalence class of A naught. So basically, you take all the knots in the equivalence class, you look at how many crossings each knot in that equivalence class has, and then you pick the number that is the smallest out of all of those. That is going to be an invariant. It's almost by definition you can see that it's an invariant because it's defined on taking all of the equivalence classes. Okay, there's another invariant. Invariant 2, key colorings. So this goes into graph theory. So let E be a prime number. Okay, then whether or not a knot is P colorable is an invariant. Okay, and this goes to exercise. Exercise 4 proves that
Sorry, I have a question.
Yeah.
With invariant 2, you say then whether or not a knot is P colorable is an invariant.
Mm-hmm.
I'm not sure how I'm supposed to interpret that.
So let's say you have the trefoil knot, for example. The trefoil knot, we have something like this. Ignore my bad drawing. We have a trefoil knot. The trefoil knot is 3 colorable, but the unknot is not 3 colorable. So let's see. Let's actually 3 color the trefoil knot. So let's take this. You can have one color here, which goes like this. For here. And then we have another color. Let's see. Let's change the color
Because
to.
there are like 3 planes that are visible.
I guess I should say the diagram, the diagram of the knot is three colorable or something. So does that make more sense? Being having a diagram that's three colorable, not the knot itself, the diagram, the projection. Yeah. So having a diagram being three colorable, for example, the diagram of the trefoil knot in R2 is three colorable, but the unknot is not three colorable. So they definitely are not going to be equivalent knots. So I won't bore you with trying to three color this, but it'll be a fun exercise to try and three color the trefoil knot. Prove that key colorings of diagrams of knots are invariant. Hint, use Reidemeister's. Use Reidemeister. Use that theorem. Okay. So now, one theorem that's actually going to be very useful later is the Jordan curve theorem. So Jordan curve theorem. Okay. This says that every embedded circle let's see, where am I? Every embedded circle in R2 bounds an embedded disk in R2. Okay. It looks like we might have to create a new what's it called, slide soon. Okay, so what you might think that this is obvious, but this is a very much not obvious theorem. For example, we go all the way up to that paradox or that wild embedding right here, the wild embedding of knots. How can it be shown that this knot or wild embeddings, so like space filling curves even, how can it be shown that space filling curves or things that look like space filling curves, they're like fractals, how can it be shown that all of those bound a disk? So the question is, oops, did it freeze? Okay, the question is, how do those curves embed, or how do those curves bound disks? And it's a very non-trivial fact. So here's a proof. Okay. So one thing you'll need is the categorical notion. Needs the categorical notion of needs the notion of inverse limit. Okay. So we need inverse limits. Okay. So take a combinatorial knot. A combinatorial. I'll just write it as home. Come on. There we go. Take a combinatorial knot in R2. And parameterize it by a path gamma going from 0, 1, sending 0 and 1 to k and the start and end point respectively. The start and end point are the same. Okay, so take a path and parameterize it. Okay, we're going to define a recursive set that xi to be, or x by x1, 1 to equal the set 0, 1 half, 1, x2 to be the set 0, 1 fourth, 1 half, 3 fourths, 1, x3 to be the set 0, 1 eighth, 1 fourth, 3 eighths, 1 half, 5 eighths, 3 fourths, and 7 eighths, and 1. And so keep doing that. So on. Okay. Okay, it looks like I am going to really quick go to. It seems to have frozen. Oops. There we go. Okay. We define these recursive sets by chopping up the line in halves and then chopping up those halves and halves, chopping up those halves and halves and halves, and so on. Those are the sets. Okay. We define a knot ki by taking for each I in the natural numbers by taking gamma of xi. So taking all these vertices, or we're going to write these as vertices of ki, vertices of ki, and the edges being interpolated. Oh, okay, let's create a new page. Oops, let me create a new page so that we can. Okay. Oh, I just need to create a new. Let me create a new slide. So let me. Oops. 1 second. Sorry for the technical difficulties. Oops. Let me get the whiteboard back up, and then I will continue. Okay.
No worries. Take your time.
Okay. Okay. Let me share my screen again. Okay. So what we did is we took the xi which is equal to just cutting up the thing, cutting up the interval. We took gamma of xi, and then so that's going to be our vertex set of ki, and then for each a b in xi squared, so taking pairs of numbers, I guess xi squared, where a is less than b and b is minimal. Draw or take an edge, take the edge in R cubed from gamma of A to gamma of B. So what am I doing here? I am taking the interval, I'm cutting it up into halves, those halves into halves, those halves into halves, so on. And then so let's call this A and B. I'm going to take gamma of A and B. Let's say it looks something like, let's say, gamma of A and gamma of B. Let's say our gamma takes the interval and maps it to something like a weird knot. Say it maps it to this. And it takes gamma of A to this point here and gamma of B to this point here. Well, then what we're going to do is we're just going to take those points and then draw a line between it. These give us an approximation of our knots. And then we do that for every point on these xi's. So then you'd maybe have a point here, and so you'd have a point here, here. You might have a point here and here and here. And so you might have something that looks like these are an approximation of our knot in some sense. Might get something like a knot that is going to be approximated by, if we take higher and higher refinements, we're going to approximate this knot. Okay, and then we note that for a high enough I in the natural numbers, ki plus 1 is isotopic to ki. Okay, and so what we're going to do is we can take the isotopy hi that goes from ki plus 1 to ki, and take fi plus 1 I to be equal hi of x1. So that's just saying take points from ki plus 1 and move them to be points on ki linearly. Okay. We can, since every loop in R3 is null homotopic, which means that the homotopy contracts to a point, we can extend fi plus 1 I to a linear, to a map, map fi plus 1 I tilde going from a disk, which we would call d squared I plus 1 to d squared I, which is the disk that fills in ki and ki plus 1 respectively. We can extend it by isotopy, by a null isotopy. null isotopies. Okay. Null isotopies means it's just an isotopy, or by null, I guess I should say null homotopies. They're not isotopies. By null homotopies. Linear homotopies. There we go. Okay. So we now, what we did is we might have an approximation of our knot here. So maybe this is Ki, and this is maybe Ki plus 1. Okay, it's a better approximation of our knot. We have a map that sends Ki to Ki plus 1 by taking this vertex here and moving it to this vertex here. Well, what we're doing is we're taking the disk that fills in Ki plus 1. So we're extending this map to the disk that fills in Ki plus 1 to the disk that fills in Ki. Okay. And so we take the inverse limit, C to be the inverse limit over I in the natural numbers of these d squared I plus 1 to fi plus 1 I tilde. And what this really is this is the intersection from I in the natural numbers of the d squared I plus 1. We want to show that this is homeomorphic to a disk, though. Okay. So we have. So basically, the sketch of showing that C is homeomorphic to a disk. We want to show that this is homeomorphic to some disk. Well, the way we do it is we know that there are linear what's it called? The simplicial disk, which looks literally just like a triangle filled in, and we have a linear homomorphism